This is ON12 P21 question 1, which tests our understanding about terminal velocity. So very first thing, what is acceleration? Acceleration, you should know, is dv dt, which is also called the rate of change. So let's write that out. Rate of change of velocity. This is the best and safest way to write your answer. Don't say change in velocity over time. I mean, sometimes it's accepted, sometimes it's not. So the safest, rate of change, rate of change, rate of change. Okay, Newton's first law of motion. What is first law? First law of motion is related to inertia. If your object is chilling here at rest, it's just gonna stay there. If your object is moving at a constant speed, constant, and if nobody else push it or stop it, it's going to keep moving at the same speed. So how we say that? First law of motion, an object continues at constant velocity. Means no changing direction. Velocity matters, direction, right? At constant velocity or remains at rest. Also meaning constant velocity. Okay, at rest means V0. Not moving, unless acted on by a resultant force. Okay, so you gotta write that thing. That's a general explanation of first law. So what we have now is a beautiful graph of a parachutist falling from an aircraft. So you jump out of an aeroplane, you go down. And you get faster and faster. Very nice graph. Okay, what do we need to do with this graph? First things first. Calculate the distance traveled by the parachutist in the first 3 seconds of the motion. You want to find distance. That would be the area under the VT graph. For the first 3 seconds. Okay, so first 3 seconds. Where would that be? Oh my goodness, this graph is so hard to read. Okay, I'm going to try my best. This is 2, 4, 6, 8, 10. So 3, I'm guessing, is somewhere. Oh my word. Oh, sorry, this is 4. Where is 3? 3 is something in between here, right? Dang, why do you give me such a hard graph to read? On a computer. If you have the paper, please zoom in a bit. So it's roughly, okay, thankfully it's a nice intercept. So you need to find what is this area, this triangle area. I'm not gonna show the every step by step. I'm just gonna highlight for you approximately. So the base we know is gonna be 3. The height goes up until this level, which looks like 29. Or somewhere between 29 and 30. So there's a allowed range of values. So you pick one as long as it's somewhere between 29 and 30, you're good. So when you find the area of a triangle, 3 seconds, and this one is about 29 or 30 meters per second. So distance is area, which is half base height. I think I should go with the 29, right? Okay lah, let's go with that. Let's go with 29. You can choose to go with 30, that's fine too. So your final value you should get is about 43.5 if you use 29. So I could round it off to 44, somewhere there, if I wanted to. So 1 mark comes from you knowing that, area under the graph, attempt to find that, and then final answer. So if you use something else, anything between 29 and 30 is okay. So your final value you can get between 43.5 and 45 is okay. It's a graph, it's hard to read, we understand. Cambridge understand. Here comes the part where you have to explain. We need to explain the variation of the okay, explain is a keyword. How does the resultant force change from point A to point C? So when we say explain force, we need to talk about who make up the force. So if we talk about force, net force will be an addition of weight and drag force, which is, by the way, in the opposite direction. So if your object here, weight is pointing down, let's call this positive to follow the graph, since velocity is positive, right? And drag force, which is upwards, let's call this negative. Where is A to C? What is happening from A to C? So from A to C, What is the process when you reach terminal velocity? Okay, the one changing is drag force, not weight. Weight is constant. So how can we write this? First thing you want to say is the equation that we just wrote. Explain resultant force. Who make up the resultant force? So we say resultant or net force is weight minus the drag force or frictional force. So you can either say drag or frictional force. Just state Newton's second law. Who make up the resultant force? Then you say who is the one changing? Drag force is the one changing. Weight is constant already. So we're going to say that the frictional or drag force increases with speed. As you get faster and faster, the drag force is getting bigger and bigger. Ooh. So what happened? So at some point, when you reach point C, what is happening at point C? Here, no acceleration already. Gradient is 0. Why? Net force is 0. Why? Because at this point C, B to C, the weight downwards is exactly same as the drag force upwards. Maybe this one is 10 Newton. I don't know. I just create a value. 10 Newton. Cancel out. No more resultant force. So we're going to say drag force increases with speed. Then we tell a story. At T0, drag is 0, but at T15, which is point C, drag is same magnitude as weight. So that's kind of summarizing up the whole change in drag. So once again, who caused variation in resultant force? The drag force here on the left side. Okay, so these are also happen to be the main 3 main points. Your points can be different order as long as you talk about these 3 main points. So who forms the resultant force? What affects the resultant force, which is speed? And lastly, how does the resultant force change due to drag? So drag is the one changing here. That's the last one. The next few questions, if you haven't tried it out yet, I encourage you to pause the video, maybe try to write out some explanations, see if you manage to think carefully what they are asking for, and come back and we look at the question together. Okay, describe the changes to frictional force, drag force. They call it frictional force. Maybe we should stick with that. Okay, sure. So changes, frictional force at C. At C, what's happening at C? At point C, it's a sudden drop in velocity. That is because that's a moment where your parachute opens. The person is like, yay, I pull the string. Then the parachute opens up. Boom. That's already a drop in velocity. So when we say describe at C, describe means you tell a story. What happens before C? What happens after C? Describe, tell a story. Okay, so let's go and tell a story what happens at C. So in the process, when you open parachute, what happens to the drag force? Drag force at first is some value that is same as weight. The moment you open parachute, boom, drag force increase. So we say the drag, or if you want to use their language, frictional force increases in that process. If you want to add a little bit more, explain, sure, why not? Due to opening of parachute. There we go. So that kind of tells around point C what happens. So this is going to be 1 mark if you talk about increases. Then they ask you, what are the changes, once again, between point C and point E? Point C and point E. Okay, we got to go back here. So point C is when you open parachute. Now we want to say from C onwards to somewhere C, D, E. Okay, this entire journey here. What happened to the drag force? Parachute is so big. So you slow down. And you slow down, the drag force also decrease. Okay. Let's tell a story about what happens here until you reach E, which is where the object has a drag force that is exactly same as weight again. Somewhere in this process, the drag force is decreasing. Getting smaller and smaller. Due to slowing speed. Okay, so here, this is how many marks are? 1 mark. How shall we explain this? I think we will say, at first, for one instant in time, very short instant in time, the frictional force or drag force is constant for a very short amount of time. This is between C and D. Miss, how you know frictional force is constant? Okay, wait. We write first. Constant, and then it decreases. Then decreases. Why don't you say equal to weight? Okay lah, we say until it is same magnitude as the weight. And this is during the section D to E. So constant and then decreases. That one, then only they will give you 1 mark. So why is there a constant here and then only decrease? This one is because I look at the shape of the graph. C to D and then D to E. If you look at C to D, it's actually a straight line, you know. So I'm going to highlight C to D first. Here. This is a constant, not straight line, constant gradient. Constant gradient, which also means a constant acceleration, which means a constant net force or resultant force. Everything, all of this, all constant. So that means, if I think of the net force, who adds up to the net force? All right, net force is weight and D. So if net force is constant, means everything here is all constant. Nobody's changing yet. So for a short moment in time, drag force is constant, very large, and then it starts to decrease. That's where we go to this part down here. So I'm going to highlight it in blue, I suppose. And here we say gradient, which is also acceleration, decreases. Because net force decreases. Because drag force decreases. All decreasing, all changing. Okay, go check out the previous video of the thing if you feel like, I don't remember all these details. Go check it out, take some notes. Alright, we are done with the explanation. Let's go to the calculation here. So now they give us a mass of the parachutist, 95 kg. Calculate between C and D the average acceleration. Before I even look at the graph, I see acceleration. Acceleration is gradient of VT graph, which means I need to find, in order to find the acceleration, which is the gradient, I need to find what is the change in velocity over the change in time. So the change in velocity over change in time, need to read the velocity change, but the change in time I know is 17 seconds minus 15 seconds. This is in seconds. Okay, from C to D, what's the change in velocity? Let's go read the graph. C. Okay, so at C, your velocity is 50. D, your velocity, I think, dropped down to 20. And it's a nice pink color straight line graph, so you can find the gradient very nicely. Okay, very good. Thankfully, they give straight line at that section. It's not very hard to find. Oh, okay, let's see. So we go from 50, drop down to 20. So we take final minus initial. This will be meters per second. Okay, what value do we get here? I should get about 15 meters per second square, but it's going to be negative. So don't panic if you didn't write the negative. You can write 15 or negative 15. They don't really care about the sign here, so that's kind of nice. If you got put 15 or no 15 is okay. So this one mark for you to find gradient. I see like you're trying to find the gradient of a graph, and if you got the correct answer, that's the last one. So in the graph, you notice all the values are positive, right? The graph is only in the positive part. So something like this is all in the positive part of velocity. That tells me that their system that they define is anything that moves down is positive. That direction. So anything that moves up is negative. So if you see this acceleration is negative, it just tells me that, at this moment in time, when you open parachute, your acceleration is upwards. So I can draw the object. Here's the weight. Here's a big drag force. And because of that big drag force, net force is upwards. Acceleration is upwards. All upwards. Which is negative. You define system. Okay. So from here, you got acceleration. Please define the average frictional force. There's only one equation we can use to find forces. That's our good old Newton's second law. So let's start with that. Newton's second law says the net force equals to mass times acceleration if mass is constant. Then we look at the system. If we stick to the graph system of signs, who is pointing up? Drag force. Okay, I'm going to give that a negative sign. See on the top, weight is downwards. I'm going to give it a positive. So we just add together all the forces. So downwards, weight minus or plus the other force, which is negative d, is going to be the mass times acceleration. Then the mass they give to us just now, right? What's the mass? 95 kg. Okay. So the weight equals to mg minus d equals to ma. This will be 95 times 9.81 minus drag force, I suppose. The frictional force equals to 95 kg times the acceleration at that point. We stick to the same system, right? Let's give it a negative sign then. Okay, so with this, we should get a d value of about 2356.95. 2357 Newton. I can choose to run out to 2 SF, and that will give me about 2400 Newton, which is also okay if you write it in 2 SF. So this is final answer. Where do the other marks come from though? The first one comes from you writing out Newton's second law equation. What minus what equals to what? Add up all the forces. And if you actually submit the correct values, that's one more mark. So here the danger is the negative sign. If we didn't include the negative sign, we might get some other wrong value. And you say, Miss, what if I didn't include a negative sign? My system is different. Can I still do this question? Yes, you can. Or, so let's choose a different system from what the current one was. So currently it was negative up, positive down, right? Okay. So if I say up is positive, down is negative, then if I write on Newton's second law, it's going to be downwards is the weight, right? So negative W plus, who is pointing up? Drag force, okay, D, equals to MA. Acceleration, from previous, we already know it's going to be upwards. So, upwards is positive. Okay, fine. No need to change anything. So this will be negative mg plus d equals to ma. So it's like, Miss, this one is kind of like the same thing as just now, right? Okay, can. We write the same thing. 95 times 9.81 plus d equals to 95 times 15. Because acceleration is upwards and upwards is positive. So you do this, you will still get the same value. 2400 Newton for the drag force. And it's more of a matter of the sign. You choose a system, you stick with it, but make sure to know which direction is which. Otherwise, something somewhere will go wrong. So I think that's the end of the official question. How you can interpret a graph, explain it, and then calculate it. Now this last part, sketch the acceleration time graph of the parachutist. It's more of a little activity. Like if we stare at this velocity graph, it's kind of chopped off. Now let's see how to think of acceleration. We already write a few about acceleration. Let's start from the beginning again. So acceleration is gradient. Gradient at the beginning, for this particular terminal velocity graph, it looks like it's a straight line at the beginning, and so the acceleration is constant actually. So you start off with a constant acceleration for a little bit, and then the acceleration, which is the gradient, will start to decrease. So I'm going to draw gradient at that point. It's decreasing. So acceleration decreases as you move along in time. Eventually, between B and C is perfectly flat. That's acceleration 0. Okay. Then suddenly acceleration changed sign because now you're going downhill. So this is negative acceleration. By the way, the left side is positive acceleration. So it's constant until we reach point D. Then acceleration starts to decrease. A negative acceleration decreasing. Because it gets flatter and flatter. Okay. And then eventually you reach some further point here. Acceleration is 0 next to my head. So we take all this information. We could roughly sketch out some kind of shape that looks like... Wow, this one's a bit hard to draw. Okay, let's try our best. So we start off at 9.81. Positive. Downwards. Then it's constant for a short moment in time. So maybe I could, for this particular graph, I could draw it horizontal a bit first. Oh man, it's already not horizontal. And then only it starts to decrease. So it decrease until 0. This is where you hit terminal velocity. So this is point C. This is point, I think, B. And this is point A. Then when you open parachute, suddenly you have a big acceleration. It's constant for a while though. And it's roughly the same magnitude. So I can't have to draw a sudden change. A sudden sharp change. Maybe this is pretty big. Could be a small, big. I don't know. I don't know what's the value. You have to go and find the acceleration. I'm guessing it should be around 9.81 as well. And then it starts to decrease. So it decreases again. So this one will be a point D, constant for a while and then decrease. And then eventually you reach terminal velocity. That's point E. So these acceleration graphs, they may vary very slightly, but generally the characteristics, the main characteristics are there. You start off at 9.81, you decrease to 0. Then you become negative. Acceleration goes to the negative part and then decrease to 0 again. For a challenge, you could try think of how would what's a challenging graph to draw? How would a displacement time graph look like? Oh, this one is going to be challenging. So this will be displacement against time as you fall from some super high up place all the way to the ground. I mean, with a parachute, of course. So we know that throughout the entire journey, if we say the top part here is 0 displacement and we go down is positive displacement, you will get further and further away, confirm. So the graph, whatever shape it should be, should increase. Maybe like this, maybe like this, maybe, I don't know. But it should increase all the time. You are always going away from the 0 reference point. So in the beginning, your velocity increases. So V increases until constant terminal velocity. So I could maybe draw something like this and then constant. How I know constant? I try to draw a straight line. Oh my goodness, it's so hard to draw. Okay, imagine this is a straight line. So increase until constant. Then, when you open parachute, the V decrease suddenly. My hair blocking again. Let's put it here. So V decrease suddenly when parachute open. So I need to suddenly change the velocity. So maybe here there'll be a bend and then I'm at a lower velocity, but I'm still going further and further away. So this is a very rough sketch of how you can see it lah. The second terminal velocity is going to be here. After open parachute, the first terminal velocity is here. And these are the sections where the velocity is constant. That's why gradient is constant. That's why it's a straight line or attempted straight line. This spot where there's a sudden bump is where the parachute is opened. And you see the velocity is curving. Well, the velocity is decreased, so that's why you have this curve, gradient decrease. Gradient here, decrease idea. Beginning, you must start off with a 0 gradient now, by the way. Down here, 0 gradient, 0 velocity. Then the gradient slowly start to increase, so V increase. So think about gradient and how it relates to displacement. Very rare they'll ask this question now, but it's just a fun exercise to think about your kinematics graph. So that's all for this question, extension and all. Hope that was helpful in better understanding how you do terminal velocity. But that's all for this video. I will see you in the next question.